Hey guys, so in previous videos we talked about collector flows. What size collector do we need for our exhaust? We talked about CFM. How much CFM does my cylinder head need to be able to flow? How do I help crutch that with camshaft selection? Okay, now we're going to talk about header selection and all the things that go into selecting a header. This video is going to be two parts. The first part is going to be I'm going to give you some old school formulas that'll help get you close. And if that's all you care about, I'm going to give those to you and you can do with them however you want. For the rest of you that are a little bit more interested in the science behind it, we're going to talk a little bit more technical and go into how I chose what I chose for Old Red. Alright, so I'm going to go over to the board. I'm going to zoom this out a little bit. Alright, so old school formulas first. Okay, so Old Red has 1 3/4 inch header primary tubes with 32-inch length primary and 3-inch collector. Okay, so old school ballpark formulas. So primary pipe cross-sectional area, calculate that first. So if you have a 350 cubic inch engine, okay, put that in divided by 8. That's that number. Multiply that by peak torque RPM. If you don't know what this is, what do you want it to be? Divide that by 88,200. That'll give you a number here. Okay, this is your area. Okay, cross-sectional area. So 355 small block. I have peak torque around 5,000 RPM, 88,200, and that's your area. Pipe size. Okay, and I don't care about units. I don't have enough board space to put units for everything, so you'll be all right. Pipe size, 2 times square root of the area we just calculated, divided by pi. Okay, so get that, 1.79. Pretty close to my 1 3/4 inch primary tube, so pretty close. All right, primary tube length, 850 times 360 times advertised exhaust valve open. Okay, do not use your at 50 thousandths number. Use the advertised exhaust valve open. Okay, this is before bottom dead center. So put that number in, divide that by peak power RPM. Okay, 850 times 360 minus 83 degrees before bottom dead center is when my exhaust valve starts to open, and divide that by 6,700 RPM, which is pretty much where I make peak power naturally aspirated, more like 62, 6,300 under boost, and minus the 3, which I didn't say, 32-inch length. Hey, pretty freaking close. Okay, collector diameter, 1.9 times the diameter of the primary pipe, 3.4 inches. So a little bigger than what I'm running. There's a reason for that, but that'll get you close. Collector length, 0.5 times primary tube length. Okay, so 0.5 times 32 is 16 inches. What this 16 inches is if you're running straight headers, you want to have a minimum of 16 inches past the collector. Okay, the reason you want that is due to velocity and all the things that I'm going to kind of go over. But if you run full exhaust, ignore this number because it means nothing to you. But if you are a race car, drag car, and you have all this set up, you want to have a minimum of this number past the collector. Okay, remember this is old school formula, it's not super technical, but it gets you pretty close. Minimum of 16 inches past the collector to maintain velocity enough to maximize your power and torque. Okay, shorter than that number, torque's going to go down. Okay, guaranteed. Now, that's the first part of this video. So for some of you, if this is all you care about, I'll zoom this out to where you can get all these generic formulas, and they'll get you pretty close, and they'll be good for most people. Now, if you're watching this video to learn and you want to go over a little bit more technical detail, we're going to shift over here. Okay, I didn't do a really good job managing my board, but that's because ideas just started flowing and I wanted to get it all on the board. So obviously I took up way too much space with the generic formulas, but anyway. Alright, so in a previous video we talked about, for Old Red, how I figure out how much CFM, okay, for each tube. Okay, so this number times 8 is the number we calculated that I need to have for the engine at the RPM, at peak RPM, which was 6,230 RPM. Okay, due to my boost and all the things. All right, so I'm not going to go into this number. You can watch that video to get this number. So this is just pi r squared. That's all this is. And you got to use the right units, okay? This is CFM, cubic foot per minute, so we can't use the inches. You have to convert that to foot. So 1.75 divided by 12 gets you what that is in feet. So pi times the radius, which would be, this is the diameter, in feet, divided by 2, okay? That gets you your radius, and then squared. So this is just pi r squared, okay? And then that'll get you 45,776 feet per minute of velocity, okay? So we calculated that. Flow rate times pipe diameter in feet divided by 2 squared, all right? Now, time the valve is open. This is where a lot of people don't realize how little time there is, okay? So at 6,230 RPM, for every 2 revolutions of the crank, the intake valve is open. So you got to divide that by 2, okay? We didn't do that for CFM, and there was reasons for that, but in this instance, we have to. So 6,230 divided by 2, because the intake valve opened 1 time for every 2 revolutions of the crank. That's 3115 RPM, okay? Divide that by 60 seconds to get you rotations per minute, 2 seconds. So that means 52 times, okay, that intake valve is opening a second. All right, that's a lot. All right, so 1 divided by 52, that gives us 0.019 seconds open. So for every time the crank turns over twice, our intake valve is only open 0.019 seconds, okay? That is not a long time, okay? So that's a perspective thing for some people. They don't really calculate that and don't really realize how violent it is and why valve spring selection is so critical. All right, now this looks like a lot of jumbled mess, and I'm gonna walk through it, okay? So the black part is what we're looking at first. So this is just 1.5 inch, 1 5/8 inch, 1 3/4 inch, okay? And this is just converted to actual inches, okay? Now, all I did was I filled these numbers right here, 1.5, 1.625, all these numbers here into this formula, replace this 1.75 to get the numbers, velocity for each one of those, okay? And that's in feet per minute. But we're not going to work with feet per minute. We're going to work with feet per second. So you just divide all these by 60, and that's this top number. There's 2 numbers in each one of these squares, but it's the top number, okay? We'll talk about the bottom number in just a few minutes. All right, and this other column we'll talk about in just a few minutes. They all go hand in hand, all right? So that just gives us feet per second. We're going to need that for the next part of this, okay? So now we're going to shift. All right, so what we got to calculate before I go any further, what we're going to do is I'm going to go through some formulas, and these formulas are used to figure out how much back pressure I will have in the exhaust. Back pressure is just a measure of restriction in the exhaust. You want to minimize back pressure. I don't know, there's so many myths out there, you got to have back pressure. That's complete garbage, okay? Turbo systems and stuff, it's more critical for them to get that right, and that's a ratio between your pressure ratio on your inlet side to your turbine housing. We're not going into that. If you have questions about that, you can send me a comment and we'll go into a little bit more of a discussion. I'm talking naturally aspirated, supercharged, nitrous, not turbochargers, okay? So you treat superchargers and everything just like naturally aspirated for this kind of math. So we're just going to go into it this way. So back pressure. Pressure and velocity are inversely related. Okay? Pressure and volume are inversely related. So the pressure and volume inverse relationship is Boyle's law. Okay? Bernoulli's principle, pressure and velocity are inversely related. Okay? Two tails of the same thing, but Boyle's law and Bernoulli's principle. We're talking Bernoulli's principle. Obviously, volume is affected by velocity. All right, so those are directly related, velocity and flow. Okay, all right. So back pressure, bad. Velocity, good. We need to maximize the velocity while minimizing back pressure. The problem is, the higher the velocity, the more back pressure you're going to have. So it's a balancing act, and that is what we're going to talk about. First, we're going to go through the math on how we get to back pressure, because that's the complicated part. And then once we have back pressure, how we get that into affecting our velocity numbers and how we use that to figure out what we need. Okay? We're going to go into it, but then I'm going to go over Darcy-Weisbach and Reynolds number and a lot of things. And we'll talk about each thing as we go through. Okay? And if you have any other questions or more clarifying stuff, just send me a comment. All right? The first thing we need to calculate is something called the Reynolds number. What Reynolds number means, and you can look this up for a more formal definition, but Reynolds number is basically the higher the Reynolds number. I talked about in my last video or a couple of videos ago, before I was talking about the supercharger on Old Red being upgraded, we talked about eddy currents. So you have laminar flow and you have turbulent flow and you have kind of that transitional area. Okay? A Reynolds number over 3,000 is considered turbulent. Okay? Some people say 4,000, but between that 2,000, 3,000, 2,000, 4,000 is kind of your transitional area. It's not a perfect science. It depends on density and all the things, okay? But Reynolds number tells us how turbulent are we, okay? How turbulent is our flow? All right, so the first thing we have to do is calculate the Reynolds number, and I'm going to do it over here, but I'm just going to talk about it first here. So we're going to get our Reynolds number, okay? And Reynolds number is nothing but velocity times diameter divided by kinetic viscosity. Now this kinetic viscosity number, I don't want to really get into on this video how we find this number, but if you're curious, I can tell you, or you can look it up. But it takes some math, okay? It's not super simple. So I don't want to get bogged down on technical discussions on how I get to each one of these things. But if you have questions, I can tell you. So Reynolds number, velocity, diameter, kinetic viscosity. After we get our Reynolds number, we need to calculate the friction factor. Okay? We use the modified Colebrook equation to get that. And that just says MOD Colebrook, but modified Colebrook. Okay? So that's 0.25 divided by base 10 log of the relative roughness of the material we're using divided by 3.7 times the diameter plus 5.74 divided by, okay, Reynolds number times 9. Okay, so the Reynolds number we calculated up here we need for the Colebrook equation. All these other numbers we have. Okay, and then you do a log base 10 of this denominator. Do not miss that step. That'll give you your friction factor. Next, the Darcy-Weisbach formula. Okay, delta P over unit length, okay, so pipe length, which is unit length, times the friction factor, or equals friction factor that we just calculated here. So we have to have that times the length times velocity squared times density. So you have to find density. Divide that by 2 times the diameter. Okay. And it's just saying answers in pounds per square foot. So we need to divide by 144 to get PSI, pounds per square inch. All right. So now we're going to put some numbers to this. So Reynolds number, and this is using the 1.75 inch, and I did this calculation for all the different ones, but we're just using my example for Old Red, and then I did the math for all the others, which are different numbers. All right, so 763, that's the number here in feet per second. Okay, I didn't write the units down on here because this is how much room I have. Then pi r squared, okay, divide that by 0.009053. Now, I'm not getting into how I got that kinetic viscosity. You're just going to have to trust me, okay? That gives us a Reynolds number of 14,078. I'm going to go ahead and go on a limb and say that's extremely turbulent, which we would expect out of the exhaust system. We got very high temperature, high pressure, and traveling at a very high velocity, so there's going to be a lot of turbulence, okay? That's a pretty critical number to have. Now, we're going to go to our modified Colebrook, okay? Modified Colebrook, log base 10, okay? So just a base 10 log, and I'm not going to go into it. We talked about all the numbers here, okay? 0.25, and we got all of our stuff. That's 3.7 times 1.75, and we're doing all 574, and our Reynolds number up here, and times 9. I ran out of room here clearly, but that'll give us 0.04311. Okay, now we're going to use our Darcy-Weisbach. Okay, Darcy-Weisbach. So delta P, unit length, 0.043. That's our friction factor. Okay, friction factor times our length times velocity squared, and this is basically your conversion. Okay, 32 inch primaries divided by 12. Divided by 12, that gets you 2.67 foot. Okay, so it's very critical that you convert your units so that all the units are speaking the same language. Okay, the friction factor is unitless, so that's not matter. You cannot use inches here because your answer is going to give you pounds per square foot. So you have to convert your 32 inch length to feet times 763 squared. That's our foot per second. Okay, so again, that has to be in feet per second. Okay, now times 0.01899, that's our density. Okay, again, in this video, I'm not going to get into how I calculated density, but if you have a question, I can tell you. You just got to trust me. 2 times 1.75 divided by 12. Okay, that converts our 1.75 inch primary to feet. Again, all this has to be feet for the units have to speak the same language. Okay, if they don't speak the same language, your data, your answer will be wrong. Okay, so we get delta P over L, which is our length, unit length. This 4357.393 is our answer with this equation. We have to divide that by 144 to convert it from pounds per square foot to pounds per square inch. So that's 30.26. Now, we have to divide that by 32, okay? And that gives us 0.946 psi. So our back pressure with our 32 inch pipe is 0.95 pounds per square inch. Okay, so down here at 5, back pressure for a 32-inch pipe at 1.75 inch diameter is 0.95 psi using our Darcy-Weisbach, okay? Real quick before Darcy-Weisbach is a formula that you use for incompressible fluids, mostly water and things of that nature. I'm going to tell you why it's relevant here, okay? Is the reality a little bit different? Yes, because we're talking about compressible gas. It's a gas, it's compressible. It does change the density per unit length. So the back pressure can be a little higher, and which will hurt flow. But I will tell you why it's relevant for what we're doing and how we choose our correct velocity, okay? I'm going to keep going, so just trust me. All right. Now, pressure, this is just what I said. Pressure and velocity are inversely related. As pressure goes up, velocity goes down. So as the back pressure, which is how much restriction in the exhaust pipe that we have for our primary pipe, due to the tube length and the diameter, okay, both things are related to this. As the back pressure goes up, velocity goes down, which means volume goes down based off Boyle's law. Okay, choose primary pipe size for velocity and length based on getting close to 1. What does that mean? Okay, first we're going to talk about this top one. Choose primary pipe size for velocity. So now this is my application. This may not be the same as your application. I have 1500 degrees of exhaust gas temperature. So if you subtract these, if you add these up and divide by 2, the difference between these is 1500, okay? 1500 degrees. So regardless, I covered this. This is the volume expansion calculation that we talked about in a previous video, so I'm not going to get into it here. Watch that video. Again, I'm going to try to put a link to it here, but this is important. You have to do this. So our target, if we're doing an intake valve, if we're flow testing an intake, you want the localized velocities everywhere in the port to be 337 feet per second, as close to this number as you can without exceeding it. It's basically 0.3 Mach. The reason for this 0.3 Mach number is I did videos on this years ago. This 0.3 Mach number is at 0.3 Mach, compressible gas behaves as an incompressible fluid. Once you get past 0.3 Mach, more eddies, more turbulence, higher Reynolds number. But at less than 337 feet per second, you can calculate it based on an incompressible fluid. So we want to target this velocity. However, we have a thermal expansion, okay, that happens in the exhaust side. So on intake side, 337 is our number. However, your thermal expansion is going to be the new target. So my thermal expansion, okay, is 2.25 multiplier. So 2.25 times 337.5 is 760 feet per second. That is my target velocity that I want. Okay, so going back to our chart over here, what is the closest to 760 feet per second? 1 3/4 inches. Okay, that is why I chose what I chose. However, we have back pressure. Okay, we're going to get into that. The next thing we have to talk about is length based on getting close to 1. Okay, so here's what we're going to talk about here. So these numbers here are just these numbers, these feet per second. Okay, I just wrote them down here. Okay, whenever your exhaust valve opens, based on it being open for only 0.019 seconds, this is how this works, okay? So 1038 feet per second multiplied by 0.019 seconds, that means when that exhaust valve opens at this velocity, the exhaust gases will travel 19 feet in 0.019 seconds. That's amazing. That's a long distance. That's outside your tailpipe. Now, we're going to get into this. So now we're going to divide that. Okay, we have to convert into feet. So 32-inch long primary pipe divided by 12. That gives us our feet. We're going to take this 19.7 divided by this number. That gives us 7.4 feet. Okay, 7.4 feet. Just stay with me. That's how far it's going to travel. Okay, this is how far it's going to travel, and then this is based on how many different pipes we have. Okay, this is not as critical right now. We're going to get into it with the next number. You're dividing that by number of paths. So in a header that has 4 primary tubes, the exhaust gas has to travel to the collector, and a reflective wave has to travel back. That's 2 paths. But how many other primary pipes do we have? 3. So that's 5 paths. Okay. The exit would be 6 paths, but we're not counting the exit because we're talking about a negative reflective wave. Negative reflective wave does not go up the main exhaust system. It only goes up the primary pipes. All right. So because it's at a higher pressure, it dissipates your lower pressure wave because 14.7 psi outside atmospheric pressure is going to be at a higher pressure. Okay, so it's going to slow you down. The only pass we care about is these 5. It's got to go down, and then 4 negative waves are going to travel up your primary pipes. Okay, that does 2 things for you. One, if you time that correctly, getting it as close to 1 as possible, you will have a negative pressure wave during the entire time the exhaust valve is open. That helps scavenge the cylinder, and during intake overlap, when the intake valve is open and the exhaust valve is open at the same time, during the overlap event, it will help pull more intake. It'll give you a higher pull on the intake at a low, because when the piston is at top dead center, you're on split overlap, okay? The piston is not traveling down the bore yet. And since the piston is not traveling down the bore yet, you do not have that delta P that is created in the cylinder to help pull the intake charge in. So if you time this correctly with your velocities, if you manage your velocities correctly, and you get this as close to 1 as you can, okay, you will maintain a negative pressure wave in the exhaust system during overlap, pulling intake charge in before the piston starts moving down the bore. That is the critical part of this, okay? So, which ones are closest to 1? You can see it here. I'm not going to do the math for all these. This is the math. You times it by how long the valve is open, okay? Divide that by your primary pipe length, converted to feet, and then divide that by number of paths, which on a V8 with a header, it's going to be 5 paths, okay? And that changes based off if you have a V6, yada, 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 okay? Now, the closest to 1 is our 763 and our 665. And those are our 1 3/4 inch and 1 7/8 inch headers, okay? If you're greater than 1, what that means is that you're going down, your negative wave is coming back up, and it's traveling a little bit further down, which means you have positive pressure at the back of the valve. Not good. That slows down that intake charge coming in. If you close at 1, you had a negative pressure wave all the way up until the valve closure. If it's greater than 1, then you're going to have positive, because of the back pressure, you're going to have greater than 1, which is going to create a positive pressure. It's going to get closer and closer to atmospheric. It's going to be equalizing. And when it equalizes, you're no longer pulling intake charge in, and you're also no longer scavenging the cylinder. So, not good. Less than 1 is okay. All right. But again, the further below 1 we get, we're not maximizing that reflective wave all the way to the back of the valve through the entire exhaust valve open event. So you want to be as close to 1 as you can on this. So these are my 2 good ones. All right. Now, last part. So doing this formula for all the different pipe sizes, we have back pressures of 2.15 psi, 1.4, 0.95, which is the one we talked about, 0.65, and 0.46. Okay, it makes sense. Back pressure goes down as the pipe gets bigger because, well, it has less restriction to flow, less Reynolds number. Okay, less velocity, lower Reynolds number, less back pressure. It makes sense. Okay. So, what are these percentages? These percentages are how impactful that back pressure is to your velocity. This means at 1038 feet per second with a 2.15 psi of back pressure, that's 21% robbing of that. So you only get the remainder. Okay, so you have to subtract 21% of this, which is 820. So feet per second is going to actually equal about 820. 765. Hey, that number looks really good. That's our close to this number. Okay, so we're going to talk about that some more. Our target number, which was perfect before, has dropped some. Okay, this one, 665, less impacted and less impacted again. Okay, so now, why is 1 3/4 inch for my application perfect? A couple of reasons. One, flow. A 1 5/8 inch primary pipe does not flow 764 CFM at my pressure. Okay, I did this on a different video, but a 1 5/8 inch is not going to flow enough volume. Velocities are good due to back pressure, but volume is not good. So this, no good. Okay, just because velocity is good, we gotta keep in mind how much volume we can flow. Okay, so 1 3/4 inch is perfect. Yes, velocities aren't optimum, but they're as close as we can get and stay at 1. Okay, the other problem with a 1 5/8 inch is not even just the fact that you have the velocities are good. It's not just because the flow is not where I want it to be for volume flow. It's also not close to 1. Now, these numbers do shift down a little bit due to the back pressure, but back pressure hasn't happened when the valve opens instantaneously during that entire sweep, but these numbers will go down. It is close to 1, but it is not 1, and the problem with this one is volume flow. Not really so much here. So the 1.1 will actually go below 1 and becomes perfect. Okay, I hope that makes sense. Okay, so pressure and volume are inversely related. Pressure and velocity are inversely related. We want to target 337 feet per second velocity in every localized velocity on the intake side. But due to thermal expansion in the exhaust system, you have to do the multiplier, and then that gives you your target. And again, you can play with the numbers, put your flow in here based off doing the math for your own application in my last video, or one of my last videos, and then work through this and use these same numbers, because these kinetic viscosities and densities and stuff, these are all based off that 1500 degrees exhaust temperature, which is pretty close for most high performance dills. So a lot of this stuff's gonna relate to you. I'm gonna get this kind of zoomed out to where you can see the whole board in case you want to take a screenshot of just all the information at once. But I hope this helps. Those are the reasons why I chose a 1 3/4 inch and a 32-inch length. You can adjust these lengths and adjust the diameters and get as close to 1 as you can given these back pressures. Now, pressures are based off of my 32-inch length and my 1 7/5 primary. These back pressures are based off a 32-inch length primary tube, obviously with these different primary diameters. Okay, so 32-inch length. So if you're using any of these diameters at 32 inches, there you go. Now, last thing about what I was saying here is, why does this matter? Well, we talked for the existing open cylinder. It also matters because you want to tune that. You tune your primary lengths. Now, Old Red has tuned. I say they're tuned. They're not really tuned. They're tuned. Tuned primary pipes just mean they're all exactly the same length. That would be perfect if the cylinder's fired in such a way that that mattered. They don't so much. So 1-8-4-3-6-5-7-2. Okay. Cylinder number 1 fires 8. Okay. 4, 3, 6, 5, 7, 2. All right. So the reason why you want to have, so for example, 5 and 7. Okay. 5 fires and then 7 fires. Well, so they're going to maximize scavenging perfectly on those, because 1 fires gives that negative reflective wave on the back of both valves at the same time. 7 fires, and as soon as 7 fires, it already has negative pressure wave in that primary to help draw out that cylinder. Great. But they're not all, because of the firing order, it doesn't really work out that way. But, it's, just one of the things. Highly tuned race engines, these tri-wise, split-wise, merge collectors, all these things, all these trick things, they only matter if you're tuning it based off of this stuff. Okay? You want that negative pressure wave to be on the back of the valve that's firing and the back of the valve that's scavenging. You want it. And if you can get that tuned perfectly, then great. Last thing, my wife has a really good sense of humor. So I want to show you my shirt. You can't really read it. It's backwards. It says, "I work hard so my truck can have a better life." I thought it was pretty funny. You might too. But anyway, hope that helps. See ya.